This was an amazing talk with Casey Moratori. We went deep into how the CPU works. He even got out his whiteboard and he was writing things down. It was absolutely incredible. So please enjoy this thing. What is this thing? I don't know what you call this thing, but it was amazing. That's what it was. So today we're going to be going over why X86 needs to die, and I'm going to be joined by Casey Moratori. Casey, can you tell us a little bit about you?
Sure. I'm fairly ancient, probably relative to most of the people on this stream. I've been programming professionally programming since 1995, and I've been in the game industry for basically all of that.
Why are we freezing?
Why the original thing we're going to talk about was the M2 exploit, and this why X86 needs to die is also kind of something I wanted to talk about.
Oh, hold on, my friend. We had to start. Okay, so this is the second time this has happened while using ping, so I'm not sure if this is a ping problem or what. So I want you to try this one more time. If you freeze again, we got to move over to Discord. But effectively, you just said, I've been programming for 1995 or since 1996, and I've been in the games industry, and then you pretty much froze at that point.
I was just saying, I've been in the game industry basically that whole time, and I'm actually currently doing a programming sort of a performance programming course on Substack that I do, and that's why this sort of stuff like X86 architecture, microarchitecture things was something that I wanted to talk about. I also want to talk about the M2 exploit, like I said, but you weren't around for that one because I think that was also a pretty interesting one as well in the news recently. But this one was also kind of making the rounds.
Yeah, this one was big enough that I saw a counter article that was like why X86 doesn't need to die. And often you don't see like article and counter articles on the internet. That means this thing had to reach a pretty high, it must have ruffled enough feathers to get people this excited.
Yeah, it was. I'm assuming you're referring to the one on chips and cheese.
I think so. Yeah, I just got linked it today.
Chips and Cheese is actually great. If for folks who don't know Chips and Cheese, it's a really cool blog where they basically post like microarchitecture analysis stuff where they'll go over like, okay, you want to know about Qualcomm Snapdragon. Well, here's like what we've sort of been reverse engineering or what they've said in their slides or whatever about how the architecture works and this and that. So for people who are interested in like how the hardware works, it's a really great blog. And they did a complete response to this shortly after it was out, and it's good. I would highly encourage people to read it. I realize that these days reading is not a thing that people do as much, but if you do read,
that's why I read. That's why I literally read full time on the internet for people.
Because, you're their reader.
I am their reader. I am their screen reader. And I also have dyslexia, which means that sometimes I'll start reading and then I just have to like stop and just take a moment because I fall apart. And I'm like, okay, guys, I can't read for like 3 minutes. I need just like to breathe out for a second.
Well, that's even more embarrassing for them. It's like he is doing your reading for you and it's harder for him than it would be for you. And you're not even doing your reading. Like, what is your excuse? You don't have one, right?
You don't have one. Well, their excuse is that I do it for them.
I guess that's true. Their excuse as well. I don't know.
It already is there.
Some dyslexic guy on the internet reads it for me, so I don't bother. Why would I bother?
Yeah,
okay.
Come on. It's the day and age of productivity, Casey.
Okay.
All right, so I'm just going to start reading through this, and then you can kind of take some bits and pieces and say, okay, let's talk about this, because the reality is that I program in Lua and Go, sometimes in Rust. Like, I'm not I would not put myself as any form of expert in any of these discussions. I have no delusions of grandeur, so this is just not my area. So it's good to have you on here that you can kind of talk about what's going on in any of the places that I'm missing.
Absolutely, and also I don't know if if it's too long to do. I don't know if you've got sections you want to read or what. I don't know how you do stuff on here because so I'll just let you. It looks
really small. It's just a bunch of comments mostly.
Okay, great.
Like, this is like pretty typical reading here. It's probably like what, 2 pages?
Go.
All right. As I'm sure many of you know, x86 architecture has been around for quite some time. It has its roots in Intel's early 8086 processor, the first in its family. Indeed, even the original 8086 inherits a small amount of architectural structure from Intel's 8-bit predecessors, dating all the way back to the 8008. But the 8086 evolved into the 186, the 286, 386, 486, and then they got names. Pentium, which would have been the 586. Oh man. Oh, I didn't even know that. Okay, well, hey, guess what's kind of exciting about this?
Yeah, this is that. So far, I don't think anyone would have any problem with the article. All of that's true. And for those of you in the chat, if there's any folks who ever read assembly language, this is actually the reason that the register names on x64 these days are so weird. If you look at the register names, if you know what that sort of stuff is, in X64, right? Because CPUs, they have these register names, which is how the
Yeah.
low level part, how it works.
XEA or something, EAX, that kind of stuff.
Yeah. So if you ever wonder where that comes from, it's because of this lineage. So the register names for the second 8 general purpose registers in the X64 make sense. They're R8, R9, R10, R11, R12, R13, R14, R15. Makes perfect sense. That's what a programmer would do, right? Why aren't the first ones R0, R1, R2, R3, R4, right? Well, the reason is because the original the original 8000, the original 8000 series, they started out with 4 registers A, B, C, and D.
Okay, so that's why it's AEX, is it's A extended.
Yes, it went from A to AX to EAX to RAX when they went from 8 to 16 to 32 to 64-bit. So all of those first 8 registers, the A, B, C, D ones, and then the source pointer, desk pointer, there's a SP, SI, etc. So that's where this comes from. Anyway.
Oh no, that's actually super interesting. Okay, so that's why. So if you're on an 8-bit one, it would have been A. If you're on 16, you're on AX, and then if you're on 32, you're on AEX, being like, oh, we're the extensions of this all. We're the Viagra of this all. And then it's like, oh no, we're on 64. So they're like, RAX, right? Is that what they did? Just kept on going?
Yes, it was A goes to AX, which has 2 parts, AL and AH for low and high, for the high, low, right? Then AX went to EAX, which you could still address the other one. So if you typed AX, you still got the bottom 16 bits, but if you got EAX, you got all 32.
Yes, and you got the bottom 16 bits, which would be in the most significant bit position because it's little endian?
Other way around. So on little endian, the bottom bits are the least significant. The ones that you see on the right side of the number.
Sorry, the front 16, the first 16 bits. If you had 32 bits, the most significant set of bits are actually the least significant values, right?
Yeah, I guess I don't know how you want to describe it, but
I'm very bad at describing endians.
Okay, okay.
Here we go. In my head, so if you had AL and AH, is that what it was? Because this would be little endian on this side, right? Is that what it was trying to be?
Written traditionally, we would flip them because the least significant ones are on the right side, and the most so the H would be you'd switch AL and AH in that diagram.
Okay, yes, but but is that how it is? Sorry, we're super digressing, but let's just keep going because I find this really interesting. Because network order would be this. Right, you have your most significant bits on this side, your least significant bits on this side. But in Intel land, this is over here and this is over here, right?
In memory order, yes. Yes, okay. But when you write a register out, right, you extend it to the 32 bits, so we write it the other way. But yes, in memory order, it would be ALAH, exactly the way you draw it the first time, which is why little endian flips them, right? Little endian, you have to draw 2 diagrams, one for the register, one for memory. Big endian is the same diagram.
Yes, I live in big endian, but I've been bitten by little endian many a times in my life.
Everything is little endian now on the hardware side, but because a lot of stuff came from big endian architectures, like you said, network order, right? It's flipped around on the wire. So
I only know things as network order, and so it's because I don't go to the machine level, so everything is network order in my brain, and so it's always just super difficult to map around.
Yep, they just wanted to make it hard for you.
I talked to an Intel guy once, and his argument was that we just drew our stacks from the top down, and so it made more sense going this way. And where other companies drew their stacks from the bottom up, and that was his argument for why little endian existed. He was some guy with 20 patents, and I was interviewing back there 15 years ago. And anyways,
there's a better argument if you want to hear it.
Yeah, I do actually want to hear this.
Suppose that you have the address of something in memory.
Yeah.
So you're just this particular byte position.
Yeah.
In little endian, that address will stay the same no matter how big the value was. If it was 8 bits, it's that address. If it's 16 bits, it's that address. If it's, et cetera, et cetera. In big endian, you're supposed to be pointing to the most significant thing. So if you make the value larger, right, the thing grows in the other direction. So if you wanted to change from going from a high one to a low one, you'd have to move the pointer.
I think I'm too stupid to understand that, but I trust you. I trust you at this point.
Okay.
All right. Along the way, new instructions were added, but the core of the x86 instruction set was retained, and a lot of the effort was spent making the same instructions faster and faster. This has become so extreme that even though the 8086 and modern Xeon processors can both run a common subset of code, the two CPUs architecturally look about as far apart as they could possibly felt like there should be another word there. So here we are today, and even the highest end x86 CPUs still support the archaic 8086 real mode, where the CPU can address memory directly without any redirection. Having this level of backwards compatibility can cause problems, especially with respect to multitasking and memory protection. But it was a feature of the previous chips, so it's a feature of the current x86 design, and there's more.
So I jump in there and say,
Yeah.
I just don't really know what this person is talking about here. Since I can't quite tell what they're trying to argue, I don't want to argue against it too stringently, but what I would point out is there's some weirdness there. So it's true that x86 CPUs support 8086 real mode. And what this means is, so if you imagine back in the day, all home computers pretty much, and of course the IBM PC as well, and so on, none of those computers even had what we would traditionally refer to nowadays as a memory management unit or memory management features. The idea that you have sort of virtual address spaces for processes, and those address spaces don't necessarily directly map to physical RAM. And so that you can do things like swap processes in and out, or check to see if a particular process should read some certain memory. In the old days, it was just like, okay, all processes, if there even are multiple processes on this thing, which, isn't necessarily even something that was supported depending on what period you're talking about, they can just read memory. It's like, I read memory, I get that physical set of bits back. So what it seems like the person's saying is like, oh, well, they still support this mode, and that seems like a really big burden or something. But I don't know any hardware company that's ever thought this was a big deal. It's just some stuff that's stuck over in microcode that you only ever hit if you need it. And direct physical addressing to RAM, you don't have to do anything additional really for that. Like if you wanted to complain about this, you might complain about having to have more segment registers or something. There are some things you could pick to complain, but the fact that they chose that I'm worrying that this person doesn't really know what they're talking about, because it doesn't make sense. For example, suppose you were just like, oh, I gotta emulate direct memory addressing on this machine that has indirect memory addressing. Well, just fill the indirect tables with direct addresses. Done. Like what was the you didn't have to add hardware to do that. It's the other way around. You have to add hardware for indirection. You have to add hardware for direct. So it sounds weird off the bat that that was their lead-in. Anyway.
Okay, yeah. And I think that, so for me being more of a layman, I think the reason why this is a good argument is that I'm like, oh man, there's a lot of legacy and backwards compatibility. I know about software, and backwards compatibility makes things worse, right? Like generally as a programmer, it makes everything worse. In fact, that was one of the big arguments why, like, if you remember the Bun and Node performance fiasco, one of the big arguments was that Node has to support all these things, whereas Bun comes in and just says, I don't support any of that crap. I do what's the current thing, that's what I support. And so they claimed that as part of the reason why they were faster.
Well, so imagine,
that's how me as a layman reads this. It's like, oh, it could be better if they just didn't support backwards compatibility.
Hardware-wise, imagine something slightly different. Imagine that someone just re-implemented Node.js on top of Bun. So anytime they could just call the fast versions, they did. And anytime they couldn't, they run some slow emulation. And then they just give you both of those things. That's more what x64 is. It's like, look, we've got the fast thing, and then we've also got this 8086 real mode that's super slow, but that's okay because you're only going to run applications from 1997 on it anyway. So who cares, right? I mean, it's earlier than that, like 1991, right, or something. I don't know what the earliest time you would still be using real mode is. Probably even the 80s, really. So, it's really not like that. It's not like, oh, it's the Node.js legacy runtime. So.
Okay. I think it's time to put a lot of the legacy of the 8086 to rest and let the modern processors run free. All right, some key terms. To understand my next arguments, you need to understand the very basics of a few concepts. Modern x86 is, to use the proper terminology, a CISC superscalar out-of-order von Neumann architecture with speculative execution. What does that all mean? Well, I do know that von Neumann plays a critical role in three body problem. So must be an important fella. I know that much. He invents the von Neumann architecture. Have you read Three Body Problem?
I have not read the Three Body Problem, but as far as I am aware, kind of in the secondary, like the feels sense of things,
Yeah.
Von Neumann is widely considered to be sort of like the greatest computer science person and very multiple other things of all time. Everyone thought the guy was kind of just next level, right?
He probably is from the future, trying to describe to us things that will happen.
There is a famous biography of him called The Man from the Future.
Not
literally.
Not shocking.
Did you know that?
No, I did not know that. Whenever someone's so far ahead of things, sometimes you're just like, am I witnessing a glitch here?
Yeah.
But okay, so if you haven't read Three Body Problem, there's this. You'll probably actually really enjoy it. Midway through the book, they describe this thing where they actually take people, and each person holds a flag, and they actually create a computer. And horses are the bus speed, and they bus instructions. They have people that hold flags in one position. They're like cold storage, and they have this whole thing where they do they do it all. It's super super cool. And then and then they're all soldiers, and if any soldier messed up, they'd get killed. It was really really cool, and they actually process the three body problem and then determine the future. It's pretty cool. It's super super cool. Anyways, the von Neumann architectures are CPUs where both program and data exist in the same address space. This is basic ability to run programs from the same memory in which regular data is stored. There is no logical distinction between program and data memory. Is this like a Lisp argument? Did von Neumann accidentally make Lisp arguments? That's a super nerdy joke. Sorry about that. Superscalar CPU cores are capable of running more than one instruction per clock cycle. This means that an X86 CPU running at 3 gigawatts is actually running more than 3 billion instructions per second on average. This goes hand in hand with the out-of-order nature of modern X86. The CPU can simply run instructions in different order than they are presented. If doing so would be faster. Can you give me a brief? This sounds like where the M1 or the M2 bug is. Can you give us a brief understanding of what they're trying to say here?
I can. Again, another paragraph that makes me nervous about the way this guy is explaining things. It scares me a little, right? That kind of sounds a little bit like a word salad to me, where they didn't quite get what they're talking about. Mm-hmm. So
they may be trying to write it for people like me, the technical person that's not technical at this level.
I don't know, because I feel like that explanation is only going to confuse you more. Right? If you came into this
speculative fetching, I don't know. I have no idea.
So, I mean, do you want me to draw a diagram? I don't know how hardcore we should get here. I can if we want to. I'm not sure if that makes sense.
How about you start with your own word salad, and if we need the meat, we'll get the board out.
Here's my word salad. So a modern CPU you can think of as there is a language, and this is really important to understand why I think this article is probably not very accurate or isn't a good representation of if X86 does need to die, this is not a very good argument that they're presenting.
Can I argue? Can I break you for 1 second? Everyone wants to see the whiteboard. If you can change your camera, if you have OBS set up and you want to go full screen here. I am willing to get your full screen right now. If you want to swap over to your desktop, we can make it happen. We have an actual whiteboard. Okay. Oh, we're going in.
So you're going to have to tell me, can you hear me from here?
Yes, we can. That is fantastic.
Okay. Can you see me drawing?
Oh my goodness. Yes, we can. Let me turn off that. There we go. Let's go. Okay.
So when you take a program, doesn't matter what it is, anything you're programming in, you said I program in Lua, I program in this or whatever. Whatever that is, at the end of the day, everything gets sent down to the CPU as machine code. And that machine code is fairly simple. It's basically something that can be described as some bits that tell you what it's supposed to do in very simple terms. So a really simple thing would be an add. There's going to be a bit pattern that says add, right?
Yeah.
Then there's going to be some information that's what are the operands. And there's either 1, 2, or 3, rarely 4. Even 3 is somewhat rare. So you'd have something like add, one of those registers we're talking about, which is a name, something like RAX, like you said. And then maybe another register or possibly even what we call an immediate, which is some values, right? All of these are bit encoded. They're all encoded as bits in machine code in the memory of the computer. And the processor is fetching those bit codes, right?
Yes. And so just to clarify, this is one of the first big revolutions, which was going from machine code to some sort of names for each one of these machine codes. So I don't have to know what RAX is. I can name it something that I can remember as a human.
Yes, and so the assembly language was the first step of that. It's a little bit easier than toggling in actual binary codes, which they used to do, right?
Yeah.
And then from there were people like Grace Hopper was famous for this, for example, who advocated for like they should be more human readable. And that's sort of why we got to where we are today, where it's people were like, let's stop having to actually put in every single instruction. Let's try to say things that are closer to what we mean and build up higher level primitives, right? And so nowadays we don't think about this as much, but this is what's actually happening in the computer.
Yeah.
No computer can execute Lua. It's executing instructions that are made to do what the Lua told you to do, right?
Yeah.
So just to be clear about what happens and where this information kind of in the article feels a little off when they described it in that sentence, they used a bunch of words there: superscalar, out of order, like pipelined, et cetera, et cetera.
Those all sound like amazing, like science fiction terms for me because I don't understand it.
We can talk about what those are if we want to in a little bit. Let me just tell you what actually happens. So what actually happens is the instruction that's going to happen, it gets decoded from that, like when the CPU is reading these instructions, it gets decoded, that bit pattern turns into something we call micro-ops. So basically this ad that you are sending down as like, I want to do this, it doesn't necessarily translate to just one thing the machine does. Mm-hmm. This is something that I don't know if the article ever addresses, but so an instruction that you encode actually can become multiple what we call micro-ops. And those micro-ops are the actual things that the CPU can do. So for example, let's suppose that this ad in x86 and x64, you can do this, had a memory address. There was some memory address here that it was going to fetch. And what this ad was going to encode is fetch this memory address, like go out, get this from a cache or from memory, right? Get this address, add it to RAX, and write it back to RAX. That's what this thing is doing, right? And to spare your viewers hours of content here, I won't explain what this means. Like, we won't go into what registers are necessarily, right?
Yeah.
But if it wants to do that, it's got multiple things it has to do. At a minimum, it's got to go fetch this memory, and then it's got to perform an add. So that might become multiple micro-ops. Like one of the micro-ops might be to fetch something from memory. Another one might be to do the actual addition. So a single instruction doesn't mean I'm just going to do this one thing. It actually means potentially do multiple things. Does that make sense so far?
Yeah, that makes perfect sense, because whenever you have to, it's just like if you're programming, if some expression do this, like, you know that there's actually a go-to in there, there's going to be a jump if it's not. Like, there's a lot of things that happen when we write, so this is completely reasonable that we just continue to abstract and make more concise things.
Yes, and people think, oh, well, this makes x86, like this, just to forecast some of the arguments, they're like, well, that's ridiculous. Okay, you're already breaking things out into smaller pieces. Obviously, x86 is stupid, because why didn't it just encode the little pieces? This was true from the very first x86. The very first x86 had micro-ops. This isn't new. They didn't accidentally screw this up. That's been true forever. And also, not only was that true forever, but all modern processors do this. Even things like ARM have exactly this thing. RISC, things people call RISC, they all have internal ops they do, and instructions that are more complicated than those ops potentially. Not always, right? Like sometimes they map one-to-one. Other times they take more. The reason for that, and again, I'm kind of jumping ahead here, but it's just coming up as we're talking about it. The reason for this makes perfect sense. What are you trying to do with this program? You're trying to, as compactly as possible, to take the least amount of memory and the least amount of bus bandwidth and cache space to transfer that memory into the CPU and use it. You're trying to represent your intentions as compactly as possible. So this is not, and never was supposed to be, a one-to-one mapping between what is in the instruction set and what goes on in the computer. It's supposed to be the most compact representation we could think of for that. And that is where this article gets, that's where this article, I think, really falls apart, is that it's not supposed to map one-to-one, and even RISC people don't think that anymore. That's not how they're going to implement a chip. So there are some things we can talk about. We'll talk about those maybe towards the end, about why there are x86 things that maybe aren't great, that it would be nice if we fixed. But I feel like the article proceeds from the incorrect premise. Anyway, now just to finish up why we came to the board. They said a bunch of other things, superscalar, out of order, etc. Well, if you think about how these things actually end up happening in the CPU, one of the things they mentioned was pipelining. And pipelining is when you want to start doing these micro-ops. I mean, we've already had pipelining even before then, because the act of turning this into micro-ops, so getting it, decoding it, turning it into which micro-ops are supposed to happen, all of that happens in stages because they're trying to crank the clock rate really high. They want to run these things at really high clock rates. And there's a limit to how much they can do inside one of those clocks, right?
Yeah.
So they're trying to crank that clock rate really high. And so what they do is they overlap. They take and they say, well, if we had to do an add instruction in one clock cycle, we'd have to clock this machine pretty low. So instead, what we're going to do is we're going to overlap the stages of fetching it, decoding it, turning it into those, micro ops, executing, doing the add on the micro ops, getting the values, writing them back. We do each of those in stages. So instead of one clock cycle, it maybe takes a total of n clock cycles, where I don't actually know the total pipeline depth, maybe 14 clock cycles or something like that, to do an instruction, even though it appears to the user that it only takes one. Why?
Okay.
Because they're pipelined. So let's say this is 14 cycles worth of length. I start my add, and it has to go through 14 cycles to complete, let's say, right?
Yeah.
Well, when it goes in on clock cycle 1 right here, it starts being fetched or decoded or whatever. It goes to the next clock cycle, it starts the next piece of work it has to do on the add. When it moves out of that first bucket, another add can be put in. So the adds are moving through this long pipeline all together. So if I put one add in every clock cycle, I'll get one add out every clock cycle. So it appears to the user of the machine that it only takes one cycle to do an add, even though it took many cycles to do one of those particular adds. Does that make sense?
This makes a lot of sense. So this is just a way, because we've hit an upper limit on how we can effectively shove things through. So we have to just get more clever. So if we can have a wider highway, if you will, we can get more cars through. Is that a very layman way to say it?
The most layman way I could think of it is, I've said this before, your washer and dryer. If any of you have a washer and dryer at home that like washes and dries clothes.
Well, we have a washer and then a dryer. We have several of them.
Okay. Think of it this way. If you didn't have a washer and dryer, suppose you just had a unit that washed and dried clothes, right? A washer dryer. You have a WD, right?
And weapon of mass washing.
It took 2 hours to do a load of laundry. Right? Takes 2 hours. Takes 2 hours to do a load of laundry, washes and dries it for you. Now I have a washer and a dryer.
Yeah.
Two separate ones like you have. Takes 1 hour to wash, 1 hour to dry. Right? Which one of these is faster at doing laundry? Well, naively, you might say it doesn't matter. Like I put it in the washer dryer, it takes 2 hours. I put it in the washer, wait an hour, put it in the dryer 1 hour, same time, 2 hours, right?
Mm-hmm.
Wrong. If I use the washer dryer, I put a load into the wash at 1 hour. After that hour's up, I put it into the dryer. How long did that load take? 2 hours. But while that load was in the dryer, and you know this intuitively because I know you've done this, you put a second load into the washer.
Yeah.
So to do 2 loads of laundry, it won't take 4 hours. It'll take 3, right?
Yeah.
We all know this intuitively. Why? Yeah. Pipelining. That's pipelining.
Okay.
Pipelining is you break up the stages of the work into smaller chunks, because once the first chunk is done, you can start a new load going in.
Okay. This makes perfect sense.
That's what this diagram is. So that's pipelining.
Okay.
Pipelining, awesome. Or the other two. Out of order. Yeah. Out of order just means, well, we take all these micro ops and we look at which ones we can do at any given time. We don't do them in order if they don't depend on each other. That's all out of order means. So the processor looks at a bunch at a time. And finally, superscalar just means it's trying to execute more than one of these at a time.
Okay.
If it can. That's it.
Very fancy terms. This makes a lot of sense.
All right. Should I say? So I guess I should stay up here, but should I come back?
You can sit down. You can sit down. You can do whatever you want. I can make you small again. If you can make it so that you can kind of go in and out easily, you may want to do that.
Okay. All right. It's just right behind me now.
Yeah, that's okay. I think people are just fine with the bright because that was awesome. Everyone's very happy about that. Okay. Everyone feels like they just got smarter. None of us are actually smarter in chat. We all feel like we got smarter.
You don't give yourself enough credit, Prime.
I don't know about that. You don't worry. You got enough credit. Okay, you got the street cred. We'll give that to you.
All right.
This was awesome. Okay, so let's keep on going. Let me pull this back up really quickly. There we go. All right. Finally, there's a speculative keyword causing all this trouble. Speculative execution is to run instructions in a branching path, despite it not being clear whether said instruction should be run in the first place. Think of it as running the code in an if statement before knowing whether the condition for said if statement is true, and reverting the state of the world if the condition turns out to be false. This is inherently risky territory because of side channel attacks. So this is like the fundamental thing that is how the M2 attack worked, right? You'd speculatively load some bits of your crypto stuff, and with enough XORing, you could kind of eventually steal someone's private keys, right?
It's actually more closely what he's describing here is it's more like Spectre and Meltdown. The M2 bug is actually part of the prefetcher, which is a memory
Up, we're losing you again. Hold on. We lost you again. Dang it. We lost you again. Hold on. I feel like if I leave you up, it seems like if I leave you running and I have your video on and I actually keep it in ping on, then you run better. So I almost feel like I have to keep you running in both places.
It might be.
Yeah, there might be some sort of optimization, some would say, going on.
Yeah,
here.
or it's prioritization in the browser or something, right? Like where it's,
This is technically an embedded browser right now I'm watching you on. It just seems like whatever's happening, if you're not on there, it breaks down elsewhere.
Well, all I was saying is that it just to distinguish between the two, Spectre and Meltdown were more about speculative execution paths, like if statements. The M2 bug, it doesn't have anything to do with an if statement. That one's just in the memory prefetcher. So that was why it was so novel, is because it's like, doesn't actually matter whether you have whether you have branches. Branch-free code will still be hit by the M2.
Okay,
we can talk about that sometime too if you want, but
yes, okay, because that's what they were talking about with that constant time programming or whatever it is. Is it?
Yep.
Is that what this is and all the fetching and all that? I understood the XOR part, and that's about it. So
okay, gotcha.
XOR is really cool. The fact that it has memory is mind blowing. All right,
XOR is awesome.
What is X86 really? Here you can see a block diagram of the microarchitectures of two seemingly completely unrelated CPUs. Don't let the looks deceive you. The Zen 4 CPU still supports real mode. It can still run 8086 programs. The 8086 is much simpler CPU. It takes multiple clock cycles to run instructions. There's an X-ray there. Anywhere from 2 to over 80. One cycle is required per byte of instruction, and one or more cycles for the calculations. There is also no concept of superscalar or out of order here. Everything takes a predetermined amount of time and happens strictly in order. Okay, so these must be the two different ones. This is the old one going on right here. I'm not really sure what I'm looking at going on here, but okay. This is probably not easy to look at.
I think they cut and pasted from the 8086 manual, diagram from the 8086 manual, yeah.
Yeah, there's just some arrows, and it looks like there's probably text here. Let me turn off. It might help me to turn off dark readers for a second.
Well, the bottom, those are just, it's just there's the segment registers in the upper left, there's the register at the bottom right, there's the prefetch, okay, sorry. Yeah, there's probably a prefetch queue, I think, in the, I can't actually see, but it doesn't, that diagram is useless. It's a useless diagram. I don't know why it's on there.
Okay, right? I have no idea what's happening here. And this also, I have no idea what's happening. Like, this just says a lot of stuff. Scheduler.
The bottom right, again, this is just why I don't understand why, like, I get nervous about whoever wrote this article. The upper left is not a diagram that actually shows the execution method of the 8086. It's not the same as the diagram in the lower right, which is showing basically like how the execution, the front end and the back end, front end on the top, back end on the bottom for the Zen 4. So it's like, again, like highly questionable article, but continue.
Okay. By contrast, Zen 4 is a monster. Not only does it have all 4 ALUs, it has 3 AGUs as well. AGU, what's that?
Address generation unit. So it's basically a thing that is, how should I put this? So when you need to access memory, you need to be able to figure out where you're getting the memory from, and that typically is like there's a thing called an effective address calculation where it's basically like take this pointer and add this much to it, and then figure out where that actually is in memory and so on. So the number of AGUs you have determines how many memory fetches you could issue per cycle. Right. Okay. So if you have 3 AGUs, you could do 3 reads in one cycle. You could issue them. They don't necessarily complete, but you could issue them.
Okay. Yes. All right. Some of you may have heard of the arithmetic and logic unit before, but address generation unit is less well known. I should have just let them tell me. All of this means that Zen 4 can, under perfect conditions, perform 4 ALU operations and 3 load/store operations per clock cycle. This makes Zen 4 a factor of 2 to 10 times faster than the 8086 at the same clock speed. If you factor in clock speed too, it becomes closer to roughly 5 to 7 orders of magnitude. Despite that, the Zen 4 CPUs still support the original 8086 instructions. So,
all of this
you've told me, so how I read this is from what you've told me. This argument doesn't have to do with this argument or this.
You are
information.
100% correct. Yes. So to put this in perspective, right? There are so many things missing from this. ALU doesn't really mean anything. It's just a way of saying there's a part of the chip that can do some computations.
Yeah,
right?
it can add and such.
But we don't even know which such. So when we say ALU, we mean, it's this part of the thing over here that can do a certain set of operations. On modern CPUs, there's a list of which operations it can do. It's like this particular one can do a multiply, an integer multiply. This other one can't. It can only do an XOR or whatever, right? I mean,
so they actually do ALUs that are hyper optimized for specific operations?
Yeah, actually, do you want to see? So I can show you. I don't know how far in the weeds you want to get here, Prime, but if I drive you towards a website for a second, can you open up a tab and go to a place called uops.info?
uops.info. This ain't porn, right?
Oh, it's wicked porn. It's porn for microarchitecture people.
All right.
And click on the thing that says table on the button bar.
And then open table?
Just click on table and open table.
I already did. Now open table. All right.
Yeah. So if you type something in, for example, add, just type in add to the search box in the left corner, right? What you will see is a list of all the permutations, the ways that add can be. So for example, if you look at add, there'll be an add like R32 or something, or R64, what those sorts of things. That'd be like a 64-bit register to another 6. Like add R32 would be like add a 32-bit register to another 32-bit register. That one you got your pointer on just a minute ago. Add R32 to M32. That's add one 32-bit register and a memory location. So fetch the memory add, right? That's what that means. It's so like once you learn to read this, you can just know what these things are. They're not like cryptic or anything. It's like, oh, okay, I get it, right?
Yeah.
Over in the column that says ports, you see that
let
says.
Let me just make sure. Let's see which one's ports.
It's the
ports way over here on this side. Yep.
Yeah, it's one that says like 1 times P, blah blah blah.
Yes.
So the P and then the bunch of numbers, P0156.
Yeah.
The 0156, those are which numerical ALUs in the system can do that operation. So they're basically saying, okay, if you want to do, like, for example, you have your mouse over one that's at M64 plus an I8, which means 64-bit memory location added to an 8-bit immediate value. So I want to take this address and I want to add this number between 0 and 255 to it, right?
Yeah.
What that string of gobbledygook says is we're going to do 1 micro-op on one of those ports, 0, 1, 5, or 6, 1 micro-op on the next port, which is 2 or 3, 1 micro-op on 4 or 9, and 1 micro-op on 7 or 8. So what that's telling you is which of the quote-unquote ALUs, ports is a more generic term that could include also the AGU, so the address generation unit part, the 2 different kinds. It's telling you which of those can handle each of the micro-ops generated from this instruction. So like I said, instructions generate multiple micro-ops. Those micro-ops can only execute on certain ports, quote unquote, which is some kind of unit in the processor. And these are them. So if you can't just say ALU, now let me show you why. The add that's doing a pure register to memory, register to value. So you look at add R16 to I16 just below you there. That's adding a 16-bit register to a 16-bit immediate. It just says it can be on port 0, 1, 5, or 6. And it's 1 micro-op. So just one thing, any of those 4 ports can do it. So that means, right? I'm sorry I'm going through this stuff so fast. I don't know how much time we have.
Can I interrupt you for a quick second? Just
Please,
so I can kind of speak from like my experience here. So what that says to me is that each one of these operations is effectively operating over a 16-bit range, because if you have a 64 and a 64, you have 4 operations, right? That'd be 64 bits, so it'd be 4 times 16. That's why this thing can operate in a single place, and 0, 1, 5, 6. These must operate in a specific memory bucket range.
No. So, you know what? I'm going to just pop back to the board real quick.
Okay, sorry. This is very interesting, but this is again way out of my depth. That's kind of how I read it. I could see that these things each are operating on 16 bits, but I don't quite understand.
I'm sorry
Quick
I'm going
math.
so fast. I just don't want to. I don't know how much time you've got, so just that's all.
We could do one more board time. I think everybody enjoys board time, so no one's going to be upset at you for doing board time.
Okay. So
You'll just have to forgive me not knowing what's happening.
no one knows this stuff. It's just not known these days, right? So that's not you. That's everybody. It's one of the reasons that I teach this stuff or try to, is because it's like good to know, because it's like demystifying. It's like, oh, I get it. Like I know how the computer actually does this stuff now, right? So those micro ops, like I said, there was like an ad or something like that. And let's take the case that we were looking at before, where it said the ad was port, like what was it, 1056 or something like that?
Yep, 1056p.
What that means, what that's telling you, is there's only one of them in that list, right? There was others that had plus ...
Mm-hmm.
Each thing separated by a plus is a micro op. So if there were 4 of them, it meant it needed 4 micro ops. So there were 4 things the CPU would have to do. This ad, the one that I think we were R16, I16, that was what we said.
Yep.
That
There's
means
only one.
That means a 16-bit register plus a 16-bit immediate. That would be something of the form add AX. We talked about that before. So a 16-bit register.
Yep.
And then a 16-bit value like 1025, let's say. Right? You can encode that in 16 bits. This is a 16-bit register. That could be an add R16, I16. It only needs 1 micro op. It can go on any of these 4 ports. What does that mean? Well, micro ops all pile into a thing that's a scheduler. And there can be multiple of these on a chip, but they pile into a thing called a scheduler, and the scheduler has all of those things we were talking about, ALUs and AGUs, different ports that we call them, P for port, that can do stuff. This is telling you that ports 0, 1, 5, and 6 all have an add unit on them. Integer add unit. So 0, 1, 2, 3, 4, 5, and 6, all of these have add units. These 2, 3, and 4 do not. So when the computer is trying to execute your add instruction, it has on any given cycle 4 places it can put it, which means it can do up to 4 adds per cycle, because if it had 4 of those to do, it has 4 things that can do it. If you want to do a 5th add on that cycle, you can't. The 5th add stalls, waiting for the other 4 because they have to go in here first. Then on the next cycle, once those adds are moving through, it can put it in one of those ports. Does that make more sense?
Yeah.
So micro ops pour into the scheduler. They sit there. They wait. This is the out of order part, right? They wait until there's available execution resources to execute them and their dependencies have been satisfied. Like you would imagine, if this register was still getting produced by some other instruction, it would have to wait till it was finished. Yep. They all pile in here. Then they all execute out when there's ports available for them to be executed.
Okay. And so I would assume this scheduler is just literally just a series of X amount of queues where each instruction can fall into these queues, and it hopefully does the best ordering possible. And that's that.
It never is going to do the best ordering possible.
Yeah,
like
hopefully.
you're trying, like you said, but it's a lot of times it doesn't matter that much because they're simple. But yeah, if you give it something tricky, there's not room on the chip in such a high performance part to have some incredibly complex like tree analysis, right? So it's just doing its best, like with some heuristics. Yeah.
Nice. Yes. Okay.
So then,
and queue management is extremely hard for anyone that's never attempted to do queue management. It's like a virtually impossible problem.
And it has all these dependencies, like I said, like, oh, I can't schedule this instruction until it's ready and all that, until the inputs for it are ready. And so anyway, that's it. And then if you have more Ps, it doesn't mean it's doing more bits. What it means is that it's doing more things. So the reason that you saw more ports on that other ad is because it involved a memory location. So it needed to use other ports to generate the address and do the fetch. So that's why you get more micro ops sometimes, is there's more parts to the instruction.
That makes sense. That makes sense because a register is already it's like an already specified kind of named location, and an I16 is a constant. So that makes sense that it can kind of just do it once versus a read, load from memory, then get those things, and then write it back out to memory.
Yep. So anyway, back to our article. The reason that I was saying that is
you have your old camera on. You got to swap scenes.
Thank you for reminding me.
Yeah.
I would have gone all day with that. Okay. So going back to the article, the reason that I was like, it's kind of weird is because it's like ALUs are not directly comparable. Like, a modern ALU is way more powerful than the 8086's ALU was, right?
Yeah.
So it's like, it doesn't make sense to compare them in the way they're comparing them. And if this is in a section where the person's trying to make a comparison to show a large multiple, well, why didn't you use the fact that like the integer multiply in x86 was like a series of ALU ops that ran one after the other? It took like 80 cycles or more. Yeah. Like, we can do those now in like 4 cycles or something or less on a, depending on what you're talking about, throughput or latency on an x64, right? So it's just weird.
Yeah. Okay, that's very good. Okay, so this is some good context to be able to understand why this is an unusual argument, shall we say, for this type of thing.
It's weird, yeah.
Yeah. So the 8086 instruction set is not the only instruction set that modern x86 supports. There are dozens of instruction sets, from the well-known floating point SSE, AVX, and other vector extensions to the obscure PAE for 32-bit x86 to have wider addresses, and VGIF, or is it GIF? VGIF for interruptions in virtualizations. According to Stefan Hewell, there may be as many as 3,600 instructions. That's more than 20 times as many instructions as RISC-V has. Even if you count all the most common RISC-V extensions. Quick question. In my head, my normal thought would be that the amount of instructions matter. Do they matter at all?
They matter very little, which is, I think, again, why this heading your section where the problem lies and then talking about something that really isn't a problem, or isn't the maiden problem, if for this type of argument, is weird. So first of all, CPUs are divided into 2 parts now. Well, there are many parts. And the part that does the instruction fetch and decode, right, that generates those micro-ops, is basically completely independent of the back end to the extent that it matters. So when you talk about adding more instructions, you're not talking about anything that affects the actual execution engine of the CPU. You're really not talking at all. You're just talking about how many different permutations of input bit patterns you plan to turn into micro-ops. That's all you're talking about, right?
Okay.
Does it matter a little bit? Yes, because if you have lots of instructions, the decoder has to be able to process all of those. But if that's your concern, what you're really concerned about is not the number of instructions, it's how specific are their permutations. Because like, if you just had a very simple bit pattern that you have to decode, right, then it's trivial to support lots of instructions. You just go like, okay, it just does these little things and that says which UOPs to do, and I'm done, right? And that part of the chip is tiny, even if it supports lots of different instruction permutations. Now, he will mention that in the article in a second here, but it's weird to not lead with that. The number of instructions just isn't that big a deal. Anyway, continue.
These instructions come at a cost. Take, for example, one of x86 oddball instructions, MPS-A DBW. This instruction is 6 to 7 bytes long and compares how different a 4-byte sequence is in multiple positions of an 11-byte sequence. Okay, it feels oddly specific. There must have been a problem there. Doing so takes at least 19 additions, but the CPU runs it in just 2 clock cycles. The first problem is the length. The combination of the 6 to 11 byte instruction length and no alignment required makes fetching the instruction a lot more expensive to do. This instruction also comes in a variant that accesses memory, which complicates decoding of the instruction. Finally, this instruction is still supported by modern CPUs, despite how rare it is to see it being used. All that uses up valuable space in cutting-edge x86 CPUs.
Which it doesn't, right? Like,
yeah, we kind of learned that there's like the separate decoder, which just I assume has that. It's just like you get this and it comes out with the micro ops.
So x86 and x64 both support memory operands. That's the thing where I said like, okay, you can do an add and you can specify memory location, right?
M64s. M32s.
M64s and M128s and 256s if you're talking about bigger registers, whatever it is, right? You can do those ops and you can support a memory address. So the fact that this one instruction has that is irrelevant to the architecture because all the instructions have that. So you wouldn't go like, oh, let me talk about that in the context of instruction. As far as the instruction being an oddball instruction, the reason these instructions exist is because they were trying to accelerate certain critical features like video decompression or compression, or AI processing. Intel doesn't throw instructions into the instruction set for their health. They do it because they have specific customers who benefit greatly from having these instructions, and that's why they're there. It's also why RISC-V doesn't have these instructions, because, hey, newsflash, nobody used RISC-V for high-performance applications, so they haven't had to deal with all of these specific cases where they need to be the fastest person on this benchmark. If they had, you better believe they would have some extension called RISC-V video decompression or whatever, where they add this exact instruction or something like that, right? So it's like, again, it's a mess of an argument, in my opinion.
Okay, that actually does make a lot of sense. In RISC architectures like MIPS, ARM, and RISC-V, the implementation of instructions is all hardware. There are dedicated logic gates for running certain instructions. The 8086 is also started this way, which would be an expensive joke if that was still the case. That's where microcode comes in. You see,
Okay, let me stop you right there.
Okay.
So this is just the person just doesn't know.
Okay.
The 8086
because you discussed that earlier about like adds being multiple instructions and microcodes and all that.
They just don't know. There are only a very small, and they're not the ones you think, set of instructions on the 8086 that aren't microcoded. Nearly every instruction, nearly every single instruction is microcoded on an 8086. So common misconception that the 8086 was simple and nope. It was microcoded and every instruction was microcoded. And if someday you want to do that on Stream Prime, I can walk you through the microcode because we know what it is now. They reverse engineered it from die shots, and we now know exactly what the microcode is for every 8086 instruction.
To be real, I'm just gonna say something. I don't want you to judge me.
I won't.
I still don't understand why they use the term die. Okay, I don't know what that means, and like my brain can't make sense of it. I've never done anything beyond microprocessors, and so I've never gotten into that level of hardware engineering. And so I don't know what it means. I know what memory maps are, don't know what that is.
So when I say you don't give yourself enough credit, Prime, I'm just going to say it right now. I have no idea why it's called a die.
Let's go.
I really don't. I can tell you what it is. I don't know why they call it a die. I've never thought about that. So when you manufacture chips, right, they're made using this lithographic process where you shoot photons at a wafer of silicon, right?
Classic, yeah.
It's this big circle of silicon. If you could probably find an image of someone holding one of them up.
There's always a circle. Someone's holding it with like gloves on in every single AI article, trying to bait you into clicking on this rainbow sheet of circle.
Yeah, and that giant disk has tons of little squares stamped on it, which are the CPUs, right? And when you cut one of those out, that's the die. That's what you call the die. Like that piece right there is called a die, I guess. And now that you're making me self-conscious, because I'm like, why the heck is it called a die? I have no idea. Now I'm gonna have to go ask a hardware guy. I'm gonna be like, dude, like, why is it called a die? I'm so ignorant.
People are saying
I don't
die
know.
casting. It's die casting. Yeah, I know. It's just in my head. I'm just like, man, there's some crazy liquid that they're spraying on wafers, and I have no idea what's happening. It's making electronics. This is crazy.
So yeah, I'm sorry. I don't know. Is it because it's die cast? Is it from the word die cast? Is that?
It's from the word die. It must be from the word die cast.
I have no idea.
I only know about the ancient molding process using clay and iron. So I have I can't go any further than that. All right.
Those would be some baller CPUs.
Those were. Fortunately, it can get worse. Let's get back to those pesky keywords, speculative and out of order. Modern x86 runs instructions out of order too, for example, to do math while waiting for a memory access. Sounds good. Let's assume for a moment that's all there is to it. When faced with a divide that uses the value of racks, followed, by the way, racks 64-bit register, right? Followed by a multiple or a multiply that overwrites racks, the multiply must logically run after the divide, even though the result of the multiply does not depend on the divide. That's where register renaming comes in. When register renaming, both can run simultaneously because the racks that the divide sees in the different physical registers than the racks that is that the multiply writes to. I kind of read that poorly. I'm kicking in with the dyslexia here for a second, but okay. So this sounds like, I mean, everything that's currently described sounds good. Like, okay, we're going to optimize it because we know that you don't overlap. Okay, this sounds good.
Yep.
This acceleration leaves us with two problems: determining which instructions depend on which others, and scheduling them optimally to run the code as fast as possible. These problems depend on the particular instructions being run, and their solution logic gets more complicated the more instructions exist. The
Nope.
X86... Ooh, no. Okay, go on. Why not?
Because it's just micro ops. So those complex instructions, like what an instruction does can be entirely boiled down to which registers does it modify as far as the scheduler is concerned. The scheduler doesn't care. It could be doing the world's most, it could be calculating all the digits of pi and, going to infinity, the infinite digit of pi, which will take the heat death of the universe, and it will grab the last digit of pi when we finally figure out it's not really infinite after all, and putting that in a register. We don't even know anything about that operation to know which registers are affected. So the scheduler doesn't care how complex the instruction is. It just needs to know, does this overwrite the destination or not? That's all it needs to know.
That makes perfect sense, because if you're scheduling a bunch of... You don't care how the food is made. You just need to know that you have enough pots you can put it into, right? And that's all you really care about. Okay.
So I have no idea what you're talking about here. I have no idea.
Okay, that makes a ton of sense. The X86 instruction encoding format is so complex, an entire wiki page is needed to serve as a TLDR. Meanwhile, RISC-V needs only 2 tables to describe the encoding of all standard instructions. Needless to say, this puts X86 at an advantage in terms of decoding logic complexity. I guess you could somewhat argue that if there's more things, that there is some level of decoding logic complexity that's more than RISC-V. But it sounds like it's not really mattering in the end.
It's true. So again, this is why I say this. I really question the person who wrote it and whether they understood exactly what was going on here, because that part is correct. The decode logic on x86 and x64 is more complicated, but it has nothing to do with whether the instructions themselves are harder to schedule or have their dependencies figured out. Those are completely separate and completely unrelated. They wouldn't even affect each other. To even make the argument that those affected each other, you have to get kind of nuts, right? Because the thing that affects...
Can I interrupt? Would the argument for it being slower or worse, would that come from the fact that decoding takes longer than the actual execution? Is that kind of this principal argument that's really coming behind this? Because if the decoder can always run faster, right? This is just like video. If your decoder can run faster than your actual renderer, you'll never worry. But if your decoder runs slower than your renderer, you'll always have dropped frames. And so is that kind of this idea that the decoding logic is so complex that it's actually slowing everything down because the decoding is slower than the execution?
So this is why, because we're at the end here, I don't know if you want to pause 1 second and just read the end, because I'm not sure that the end makes much sense. But that was what I was going to say is the one thing that is worth talking about is decoding complexity. And so we should just do that at the end as our final thing, because that is a valid point that is not made well in this article, and they don't explain to you the actual thing that matters. Anyway.
Okay. Over time, the other instruction sets like ARM have been eating at x86 market share. ARM is completely dominant in smartphones and single-board computers. It is growing in the server market, and it has even become the primary CPU architecture in Apple's devices since 2020. RISC-V is also progressively getting more popular, becoming the most widely adopted royalty-free instruction set to date. RISC-V is currently most used in microcontrollers, but is slowly growing towards higher-powered platforms like single-board computers and even desktop computers. RISC-V, being as free as it is also becoming the architecture of choice for today's computer science classes, and this will only make it more popular over time. Why? Because of its simplicity.
But it's not, right? That's not why it's popular. It's popular because it's free. Full
yes,
stop.
Well, also, just because you know one doesn't mean you can't learn another. I don't think there's any risk to Intel in this. Let's pretend Intel never would want to change for whatever reason. I obviously don't understand that. But I don't think that that's somehow an inherent walled garden that is big enough for them to have to change.
And also, ARM would be a better comparator to RISC-V. And it's look, ARM is equally simple, more or less. If you actually extended RISC-V out to be able to do all the things that ARM does, they wouldn't look all that different, right? So it's where's the argument? I don't see the argument for RISC-V adoption is pretty much just that it's free. There's your argument.
Okay. Yeah, right? And I mean that can be a good argument. Yeah.
It certainly can be. I'm not suggesting that it won't get a lot of adoption specifically because of that. But that's the argument. It has nothing to do with its simplicity.
All right, conclusion. The x86 architecture has been around for a long time, a 46-year long time. In this time, it's grown from the simple days of early microprocessors to the incredibly complex monolith of computing we have today. This evolution has taken its toll, though, by restricting one of the biggest CPU platforms to the roots of a relatively ancient instruction set, which doesn't even benefit from small code size like it did 46 years ago. The complexities of superscalar, speculative, and out-of-order execution are heavy burdens on an instruction set that is already very complex by definition, and the RISC-V shaped Grim Reapers named ARM and RISC-V are slowly catching up. I'm trying to read this as dramatically as possible. Don't get me wrong, I don't hate x86, and I'm not saying it has to die today, but one thing is clear, the days of x86 are numbered.
So in that conclusion, before we go on to the thing about the decoding, which I do want to talk about, which I think makes a good closing. So you can see why I'm nervous about the person who wrote this article in this conclusion. It sounds like, and maybe I'm mischaracterizing them, but just when you read that paragraph, I'm just saying what it sounds like they're saying. It sounds like they're saying that the x64 instruction set somehow is the only one that requires superscalar pipelined out-of-order execution. Right? I mean, am I wrong, Prime? I mean,
that's how I would read it. This is
right?
Precisely, is that these things come with this more complex one. Whereas these ones are much more simple.
But all of these architectures use that. There are no modern chips that aren't this thing, except for like really crappy, like little super low power devices no one is talking about. No phone on the planet that anyone uses or cares about isn't already on ARM and doing all three of those things. Out of order, superscalar, pipeline X2. They're all doing it. So it sounds like the person just has no idea what they're talking about when they say stuff like that. I'm like, what do you mean? Like, what's going on? So that's why it's really frustrating. You see this art. I think that's why also Chips and Cheese wrote the thing right after. So like, what is this person saying? It doesn't make any sense, right? So anyway, I'm
going to be real with you. I said from the very beginning, I think this article is directed towards normies like me, where like, when I read this, I come away with a conclusion, and it may be completely wrong or right. It doesn't matter because I can't technically argue against it, but I understand a lot of the underlying things. Like legacy typically makes things really hard. More is typically more hard than less. When you don't do a bunch of these really complicated things, you can do really simple things, right? Like all of that sounds very reasonable to me.
And, you know, like I said, unfortunately, at least for the thrust of the article, it's just really not that true. But let's talk about the one part of it that is true.
Yeah, the decoding complexity logic that was right here.
Let's talk about that. So a lot of people, I think, mistakenly think of decoding complexity as being something that's like CISC versus RISC, right? But really, they're sort of separate. You could imagine because RISC is reduced instruction set computer, just means not very many instructions, right? The instructions do simple things. And you're supposed to do multiple of them to do a complex thing. Right?
Okay. Makes sense.
Well, I could create the world's worst encoding for your 32 instruction computer that would take hours to decode instructions, right?
Yes, I see the argument.
So
yes.
They're two separate things. There's how well did you structure the decode bit patterns to be friendly to modern CPUs? And then there's how simple is the thing. And this person is conflating those two things, which often does happen. But it's important to separate them because the actual thing that's not so great about x86 or x64 now is that there are a few inherited aspects of how things are encoded that make them less desirable from a decode standpoint. And when I say from a decode standpoint, what I mean is, as you correctly surmised earlier, Prime, if I want to execute 7 instructions per clock cycle in my total throughput when I measure it, I'd better be able to decode 7 instructions per clock cycle.
Yeah.
So if actually it's very hard for me to make a chip front end that can hit that sustained rate, because I've chosen poorly how my instructions are encoded, you could imagine, and this is not that far from the actual problems in x86, imagine if I sent my instruction stream down zipped. It's a zip file, right?
Mm-hmm.
Now I have to decompress the instruction set, and as I decompress it, I can't figure out what like the next 3 instructions are all at once. I have to like decompress each bit like first to find it out, and then I can look at what they are, right? Modern things would much prefer to be able to decode all like several instructions at one time, right? They want to decode 7 at a time, 8 at a time. Later it'll be more. And so making bad decisions about that can put a lot more stress, because now they have to be like, okay, we're gonna have 2 stages, one that like decodes blocks and unzips them, and then there's another stage that does 8 at a time, and we'll try to have the unzipper be on this really fast, like separate thing, right? And you hit these bottlenecks of like, we can't just make this thing wider. We can't just do more at a time because it's all dependent on each other. X86 has some nasty elements like that. And that is the thing you would actually want to fix. You could keep the exact same instruction set. There are some other things like flags you might want to change, and whether shifts modify flags. There's all these like minutia we could change to fix things a little, but you could keep the exact same instruction set and fix that decoding aspect. And then all of the problems we're talking about in the article pretty much go away. So again, there is a problem there that would be nice to fix. It's not any of the things they're really talking about.
Okay. And that last one actually makes the most amount of sense, which is really like you have a driving force, and whatever's the slowest part of this sequence will always be the slowest part of the entire thing. And so if decoding logic truly is the driving force, then that is going to be the slowest thing. And then that's going to cause that's where your bottleneck's at. But that doesn't sound like it technically is the case today. So therefore we're safe. But does that come to a point where it can be?
It like I said, the article, there is another article you could write that is right about this, right? And that article would basically be like, look, we could be decoding a lot more instructions per second for x64 with a lot less silicon if we made these changes. And by the way, I believe Intel has proposed some things like this. Like it's not like people know that this is a thing. Like they know that there are some encoding screw ups that are due to legacy. And so there are some things you would want to fix there, where it's like, here's a way we could redo this encoding to just be a little friendlier on decode, and then these problems go away. So as it is right now, they're spending more die space, to use your favorite term again, that neither of us knows what it means.
Shooting photons, shooting light at a disk.
More of the space on that CPU is taken up by decode logic than probably should be.
Yes.
That's probably true right now. And it creates more of a struggle for x64 vendors, AMD and Intel. It creates more of a struggle for them. They have to do more work.
Space matters an incredible amount. A micrometer makes like a huge difference when it comes to this stuff.
Because you can put something else in there.
Yeah.
We can use that space for more, whatever else, more cache, more whatever and so it does matter, and it does create practical problems where, there's engineering time. There's a bunch of engineers who are spending their time figuring out how to decode instructions faster. If it was simpler, they could have been spending their time optimizing something else, right? So there is a germ of truth to it, is I guess what I want to get at, and that it's not totally, there isn't a good article. There is a good article you could have written about this topic.
Okay. So there is a really good nugget of truth within this, because I don't like to entirely just shit on something. There is a very good point, which is that this is a serious problem, but the framing and everything about it, they missed most of the time. They have a worse batting average than your Hall of Fame batter for baseball, right? Which is like what, 0.3? Right. So
not that high. Yeah,
not that high. You're not winning out there. Okay.
No.
Okay. So they win about the same rate as I win in the stock market. So good job.
They
did it. All right. Well, hey, this was a great time. Thanks, Casey, for being on here. This was a super informative, and people. I don't think I've seen people this excited about CPUs in a while.
Yeah, CPU minutia.
Yeah, CPU minutia sounds actually very, very exciting. Can we get a bunch of claps here? Yeah, and also go follow Casey on Twitter. Chips and
thank
Cheese
you
article.
very much, everyone.
Yeah,
I love talking about CPUs, so it's my pleasure.
Well, let's do another thing. Maybe I'll try to find some time. Maybe because I don't know if you know this, I'm now full time. Maybe I'll try to find, or when I say full time, I'm now fun employed. I no longer have a job. But maybe I'll try to find some time to create that 8-bit. There's like an 8-bit computer tutorial. Maybe I'll try to go through that, and then we can kind of talk about some of like how does the next steps happen? How did people go through something more advanced? Maybe, or maybe there's something we can kind of come together with that Makes a lot of
Sure.
sense.
Yeah, anything you want. I love the show. That's why I always say anytime.
Yeah. No, I think everyone loves you more than me, so you can most certainly come on. Any day of the week, you just let me know. You pick an article, you pick something, get on in here.
All right. Well, and ask the chat. If the chat likes this, they can tell you what they want us to talk about. I'm happy to talk about whatever. Obviously, I only really know microarchitecture, performance kinds of stuff. So
you know game engine stuff. You can always talk about.
I do. I know some game engine stuff too.
There's
yes.
Space-Time DB coming up. There's a lot of cool stuff, right?
Anytime, Prime. I love the show. Like I said, and so anytime.
All right, awesome. Go follow him on Twitter, and then you also have some. You release some videos and stuff like that too. Well, where can people find that?
Oh well, there is a paid thing I do that's this kind of stuff. It's
what is it?
ComputerEnhance.com.
Computer Enhance.
Yes,
.com.
like when they're like enhance that quadrant,
yes.
like that kind of thing. Yeah.
All right, let me make sure. Okay,
That's
cool.
it.
There we go.
That's it.
Let's go. All right, I'll make sure. I should make sure this happens. Sometimes I don't actually end up putting the links in my video sometimes. So I will try to remember to put the links. But for those that are still watching, ComputerEnhance.com.
I'm just happy to be on the stream, Prime. It's totally fine.
Yeah.
I just like doing it. I like doing the stream. So thanks so much for having me, and thanks everyone for watching, and I will see you guys next time.
Yeah.